In section 9.2, we're going to cover a handful of objectives. The first two are number 1 and number 2, which we did in section 1. Just evaluate nth roots in exponential or radical format, both with and without a calculator. And then number 4, we're going to apply nth root properties again to different area or volume problems. And then the two new objectives we're going to cover are 6 and 7. Objective 6 is apply nth roots to octaves in the musical scale. And you can kind of see how they're applied to a different field of study. And then number 7, evaluate powers by applying the properties of powers to them. So let's just jump into the notes. What we want to take away from section 9.2 is that we're going to be talking about rational exponents. And they look like this format right here. The word rational just means a number can be written as a fraction. An exponent is the little superscript when you have a power. This entire thing here is called a power. The little exponent, which is m divided by n, is the actual rational exponent itself. Now, what you can remember to do is property of exponents. You can write this first one by you can pull out the numerator or the m, because the property of exponents would say these two exponents here would be multiplied together. Or if you wanted to, you could actually look at it the other way. You could pull out the 1 over n and have the m on the inside. So again, when you multiply these two through, you're going to end up getting m divided by n. So let's look at some examples of how these properties would be used. This is a great application of the first objective to evaluate exponentials, rational exponents that is, without a calculator. To do this, what you could do is one of two things. That slide we just looked at said what we can do is we can take 2/3, by the way. I know 2/3 is the same as saying 2 over 1 times 1 over 3. So what you can do is break it down into two things. You can break it down into 2 over 1, and as an exponent, 2 over 1 is squared, is what that means. Or you could break it down to the 1/3. And in the exponent world, 1/3 means the third root. So what you can do is I can take the 64 to the 2/3 and write it as a 2 first and then 1/3. Or if it's easier, I can do the 1/3 first and then the 2. Now without a calculator, one of these is clearly easier to do. I personally do not know 64 squared without using a calculator. So I'm going to look at this one here. I want the cubed root of 64. Means what number 3 times gives me 64. If you think about it, the answer here is going to be a 4. So the cube root of 64 is 4. And then I still have on the outside that I need to square the answer. 4 squared is 16. So 64 to the 2/3 power is the number 16. If you needed to show work for this problem, this is sufficient enough work that I've showed. I'm clearly showing you how I've broken down and evaluated the problem. You know, for some extra practice, take a look at this. How would you do 4 to the 3/2 power without a calculator? Go ahead, pause the video, give it a try, and see if you can break this down, and then turn it back on to see what the problem looks like. If you do that, you're going to notice you get the same answer. What you can do is take 3/2 and you can break 3/2 down into 3 over 1 times 1/2. So you can either first cube the 4 and then come and take the square root, or you can take the square root of the 4 and then come in and cube that answer. Okay? Look at this QY1. Use your calculator now to estimate what the answer to this is going to be. They want you to do it for two components, for 100 to the 4th power, and then the cube root, and then the cube root of 100, and then raise that to the 4th power. Now if you realize the connection here, you can multiply the exponents here through, and you really have to find 100 to the 4/3 power. In your calculator, just do 100 to the caret key, and it's very important that in parentheses you put 4/3 as the full exponent. The new operating system will actually position itself to look like this. It'll do 100, and it'll put a little box up there that you just type the 4/3. The old operating system, you have to type it in like this. And when you do that, you should get 464.16 if you round to the hundredths position. Now I want to have us take a look at achieving objective number 6, which says apply nth roots to octaves in the musical scale. And we're just going to look at 2 slides for how this works. So here's what we have. There's the 12th roots in the musical scale is this. If the length of a string, for example, in a harp, is cut in half. So you have a length of a string, let's say it's a foot long. If you cut it in half to 6 inches long, the tone raises by an octave. So every time you take a string and cut it in half, the tone raises by 1 octave on a harp, for example, or a piano, or so forth. Most music today divides an octave into 12 notes, and they call that a chromatic scale. So one complete octave will have 12 notes within it. All right, here's our formula. Have G be the factor related to the length of the string. So G is the factor related to the length of the string, and we know that we can get 12 notes in the octave, and that octave is created when we cut the string in half. So they're giving us this relationship. So the question is, if this is the relationship, they want to know, what does G equal? Well, to solve this for G, all you have to do is come in and get rid of the exponent of 12 by doing the 1/12th power. So that's going to tell us that G, which is, again, the factor related to the length of the string, is 1/2 to the 1/12th power. And that number is approximately 0.944. Okay, that is the scale factor. So here's the deal. To move to the next scale, the string must be shortened to 94.4% of the previous length. So again, when you have from one tone here or to the next octave here, they're going to have 12 different strings in there. And what you're going to see, if you want to visualize it, again, let's say that there's 12 inches in this string, and when we do a complete octave cut, it's going to go down to 6 inches. Okay, so that's the length of the string. What's going to happen is that there's going to be 12 notes within here, so you're going to have 12 different notes taking place. And when you strum them on a harp or hit the key on the piano, those strings are going to be cut. They're cut shorter to get from the 12 inches down to the 6 inches to make the octave. And all you do is you're going to take 94.4% of the previous string, and you will get this next note. Take 94.4% of that string to get this note, and so forth. And that's where the length of the string actually comes from and how it is cut in the actual construction of a harp or a piano or so forth. Now, taking this into consideration, let's look at a word problem on how this would translate to a piano, for example. Okay, here's the scenario. It says here that the G that is 7 notes above C sounds very good with the C because the strings are close to vibrating together. So you identify those notes. This is the G right here. That is 7 notes above this C. And if you count that, here's, 1 key, 2, 3, 4, 5, 6, 7. So that's where they're saying it's G is 7 notes above the C. Okay, here's the reasoning. This is because the ratio of the lengths of the strings is very close to a simple fraction with small whole numbers in its numerator and denominator. What is the ratio? Okay, so we know that when you take a string for the C and it's cut directly in half, it's going to end right here. That's 12 notes, and that's 1 octave. Okay, so we'll go down 1 octave. And they're telling us that note C and G sound really good together. Well, there's this mathematical relationship. Okay, now what we learned on that previous slide is that we said this, that the notes are cut such that it's 1/2 to that 1/12th power, again, which was approximately that 0.944. So they want to know what is the ratio of the strings. Well, let's take the ratio and look at note G with respect to note C. Now, since we start with note C, that is the original length, so I'm just going to call that L for our original length. Well, the length of note G, we're going to take the original length of the string of C, and we're going to actually use this proportion right here. Okay. What they're going to do is they're going to take 1/2, and it's not 1/12 of the original string. Each note is 1/12, so this is going to be 1/12, 2, 3, 4/12, 5/12, 6/12, 7/12. They're going to take 7/12 of that. So if you apply this relationship, what you're going to get, simplify 1/2 to the 7/12, and you're going to get 0.667419, and that would be the relationship of L to L. The L's are kind of irrelevant here, but what it is 0.667 is approximately the fraction 2/3. So there is actually a mathematical reason of why you play on the piano notes C and G together. It sounds good because there's this great proportion, this nice simple proportion of 2/3, which just causes that good harmony. The last objective for this section is number 7, evaluate powers by applying the properties of powers. These are the properties of powers that you learned back in algebra and algebra 2x. We're just going to revisit this right here. We remember when the two exponents are right next to each other, you can multiply them. When you have two powers that you want to multiply together, you actually add their exponents. When you have two powers that are being divided, you subtract their exponents. When you have an exponent on the outside and two variables on the inside, you can kind of distribute that to it, and it can be written as x times y or x divided by y. You would still distribute it. So do reference these powers of exponents. And let's just go ahead and look at some examples of applying these powers. This problem right here, we want to combine the two powers together. Now, these two powers have the same base. They both have the base of 2, so you can combine them. If those two bases weren't the same, you couldn't combine them together. The property of exponents would say you would actually add these. And let me show you why. If we do something more simple, what if I had 2 to the 4th times 2 squared? What that logically means is this means do 2 4 times. This means do 2 2 times. And when you look at it, you're going to have 6 2s, so it's 2 to the 6th. So in basic algebra, you realize you add the exponents. Well, same thing here. So to add the exponents, you're going to do 4/3 plus 2/3. Now, these are rational exponents, and they're fractions, so you have to remember how to add fractions. Just need a common denominator, which we do have. So this is going to be 2 to the 6/3 power. Well, 6/3 is just 2, so it's 2 squared, or the answer for this problem is 4. Continuing on with that 7th objective, some other properties. Remember, when you have any base number here and you raise it to the 0 power, it's 1. So for example, 5 to the 0 power is 1. Negative exponents are not considered to be simplified. We do not want negative exponents. All you have to do to get rid of negatives, again, for example, what if we had 5 to the negative 2? You can put it over a fraction, and when you cross over that fraction bar, it becomes 1/5 squared, which is 1/25 in this case. Now in this example here, this QY3, they want us to simplify and tell us what the fraction equals. Again, this is not simplified because you cannot have a negative exponent, so I would put it over 1 and drop it down. I would get 1/8 to the 1/3. Now 1/8 to the 1/3 is the same in radical format as 1 to the cube root of 8. And it would just say, what number 3 times is 8? It's 2, so the answer to this problem is 1/2. And you would want to keep this as a fraction answer on a test or a quiz, and basically be able to show that you can do this without a calculator. You know, I'm going to challenge you to take a look at this one. This brings together some nice properties. Pause the video and see if you can get the correct answer without using your calculator. I'll have the work shown on the screen and you can see if you did it right. So go ahead and pause it and give it a try. The answer to this problem you should have gotten is 1 over 343. I would highly suggest first getting rid of the negative exponents and then look at the fraction of 3/2 and decide how you want to break it up. You can either cube first and then take the square root, or you can square root and then cube. This is going to be a lot easier to take the square root first and then cube it. So you get down to 1 over 7 cubed. Now, 7 cubed you may not know by heart. I could see maybe using a calculator for that if you needed to, but you could do the math, do 49 times 7 and get that it's 343. Keep this as a fraction, folks. Most common mistake would be people would say, oh, the answer is 343. It's not. That 7 cubed is on the bottom of the fraction, so be careful with that. Now, this isn't a nice example of, again, of just applying the properties of rational exponents and radicals. And it says here, put these in increasing order. What you're noticing of these 4 terms is that they all kind of are stated in different ways. This first term is stated, its exponent is an integer. These 2 are written as radicals, and this is basically a real number or decimal. What I would do is get them all looking at the same type of exponents. So rewrite them so they're all written in exponential format. So clearly we're going to have the x squared still. This next term becomes x to the 5th to the 1/3 power. Well, that is the same as saying x to the 5 over 3 exponent there. This next one is going to be written as x to the 1/2, and then there's 7 on the outside. This is the same as saying x to the 7/2. And then we have the last is x to the 2.8. So what we're doing is comparing these 4 here. If you like them all as decimals, go ahead and do that and change them to decimals. So we'd be comparing x squared. This would be x to the 1.67. This would be x to the 3.5, and then x to the 2.8. They want these written in increasing order. If you put them in increasing order, what you're going to end up finding is you have to realize that this number here, this particular expression will give you the largest value first. So this one will be first. The next one would end up being this particular problem here. This would be our third, and this would be our fourth. And then when you put them in increasing order, use the original format that the problem referenced. So we know x to the 3/5 power is the same as this one right here would be our cubed root of x to the 5th. The next one I had was x to the 2.8. And then we're going to have x squared. And then we wrap it up with the square root of x to the 7th power. And those are put in increasing order in terms of if I put a value in for x. If you're struggling with where that comes from, what I would suggest doing is pick a number for x, try the same value, maybe 2, and see which ones give you the largest numbers and put them in order from there. This example here is our second to last one. Again, it's just using property of exponents. I like this problem because they're challenging you to write it as the power of 2. This is currently written as a power with a base of 1/2. So that's the base of 1/2. And it's a power of, they should have said base 2 to be more specific. They want you to have it right as a base of the number 2. What you can do is apply some properties here though. Any number can be written as an exponent. 2 can be written as an exponent. It's an exponent of 1. And then don't forget this is out here. What I can do is kind of reverse my rule. I can bring this guy up, and when I bring it up, I get 2 to the negative 1/2 power, and then this is n to the 12. Property of exponents would say I could multiply these 2 and get 2 to the negative n over 12. This is written as a power of base 2, and I've completed the problem. This last problem is a great example of Objective 4 of applying nth root properties to area and volume problems. So let's just take a look at this one. Part A, they want us to find the volume of a cube that has the surface area of 105 square inches. So let's just do that. You want to recall surface area. Surface area is just that. It is the area of the surfaces. A cube has 6 surfaces. The area of a cube has squares as faces. So the formula for squares are going to be take your 2 side lengths, which happen to be the same. So take your side lengths and multiply them together. Okay, I'm going to use x for this. So the area of one face of a cube is x squared. But there's 6 of them. And I know the surface area is 105. If you solve this, divide by 6. And I'm going to keep this in exact format, so to solve for this part, take the square root. So x is actually equal to the square root of 105 over 6. That's an exact answer, by the way, and I'm going to keep it like that. So now they want us to actually find the volume, so we have to take that step. Volume of a cube is just take all the sides and square it. So take all 3 sides, and in this case they're the same. So I'm going to take my and cube it. So let's go ahead and cube that. Now what was x? It's this right here, so go ahead and pop this in for x. So the volume of the cube is going to be the square root of 105 over 6, all cubed. And to simplify that, I would just rewrite it in this format. This is 105, this is a 1/2 power, and I have a cubed out there. So the volume in this case, you could say, the volume of this particular cube is 105 over 6 to the 3/2 power. And this answers the question for finding the volume of the cube that has that surface area. Now, people may not know what this answer is, so you could type this into the calculator and get an approximate answer. And when you do that, you will get, it's approximately 73.2, we are talking inches cubed. Okay. Now, let's take a look at part B of this problem. They want us to express the volume of the cube as a function of its surface area. So let's go ahead and do that on the next slide. So for part B, let's just recall this, that the surface area of a cube that we just dealt with, this cube was 6 surfaces, x squared, and we had it was 105. And then we said, by the way, the volume is going to be our x, our side lengths cubed. Now, what they want us to do is express the volume as a function of the surface area. So it's a formula. So they're saying we don't necessarily know the surface area is 105. So I'm just going to do this. That 6x squared is equal to the surface area of our cube, whatever that is. Fine. They want us to solve or express volume. So they want us to say express volume as a function of surface area. Right now, this is the volume formula expressed as a function of side length. Okay, so it's volume with respect to side length. They want volume with respect to surface area. So they wanted to say volume equals something in here with surface area. They wanted to have SA in there, not the X. So the easiest way to do that is to solve, come back here, solve our surface area problem for X, and plug that in to this equation over here. So if we solve again this for X, we're going to divide it by 6 on both sides. So we take surface area divided by 6, and then come in and take the square root. So we know the side length is equal to the square root of the surface area over 6. Fine. Take this, which is an x, and plug it into there. When we do that, we're going to get volume is equal to, I'm just going to go, let's go right away and just write this as 1/2 power. And then we're plugging it in there and cubing it. So when we solve it, we're going to get that the volume is equal to surface area divided by 6, all to the 3/2 power. So it's basically doing part A of the problem without numbers. This is just in a formula format, and thus this is volume stated with respect to surface area. For the homework, I am just going to keep the assignment as it stands. There's some good repetitious practice in some of these problems which you are going to want to have so you remember what you learned back in Algebra 2X. Good luck.